I'm thrilled to roll out the latest episode of the Quantum Seminar series dedicated to the research and academic communities. The seminar takes place every Friday at noon Eastern Time and will be hosted on this Qiskit YouTube channel. So you can always go back and see the lectures after they're recorded. I'm your host, Zlatko Minev from IBM Quantum, and today I have the pleasure and privilege of hosting Professor Debbie Leung from the Institute for Quantum Computing at the University of Waterloo. Hello, Debbie. How are you?
Good, thank you.
Where are you tuning in from today?
From Waterloo.
All right. I'm tuning in from New York. And before we get to your talk, allow me to provide a bit of a background to the audience. Professor Debbie Leung is the University Research Chair at the IQC, Institute for Quantum Computing at Waterloo. She is also a faculty member at the Department of Combinatorics and Optimization. In 2005, she won a 10-year Tier 2 Canada Research Chair in Quantum Communications. So she's the real expert here on that. In 2002, she won the Tolman Postdoc Fellowship at the Institute for Quantum Information at Caltech, and the Groucher Fellowship and many other awards. After a BS in Physics and Math in Caltech in 1995, and she did a Ph.D. in Stanford with Professor Yamamoto and Aichuan. And I should mention that she did a 2-year stay at the Physics of Information Group at the IBM T.J. Watson Research Center in 2000. So Debbie, I think why don't we pull up your slides, and I'll ask questions from the audience during the talk. Folks, you can ask questions in the comment side box. And with that, I will turn it over to you.
Thank you so much. In fact, I have very fond memories of my 2-year postdoc at IBM, and there were some connections to this talk to my stay there as well. So I'll start with the Wikipedia definition of embezzlement. It's a theft. It's a theft by parties who are entrusted with certain assets. It's premeditated. It's done intentionally to conceal the crime, and it may continue for a long time without being detection. So these are the essential properties of embezzlement that these two characters, Wim van Dam and Patrick Hayden, imported into the quantum community. They first presented this result at the QIP at IBM in 2002 on a room session for 10 minutes. It was one of the most interesting talks I have ever seen. Instead of Wim and Patrick, I will have Alice and Bob instead in the talk, who each will be in possession of a space that remote from one another. So throughout the talk, most of the time, I will consider a two bipartite system. Alice has one space and Bob has his own space, and they're divided by a thick wall. So if they only prepare their own local state, they start out not being correlated, and they do their own things, and they perform their own measurements, then clearly their measurement outcome should be uncorrelated. In contrast, if they start with some entangled state, and then they perform their local operations and generate their measurement outcome, not only their measurement outcomes will be correlated, it's known that they can be correlated beyond any hidden local variable model, which means that they can perform things classically. They also share randomness. But it's known that entanglement allows them to generate correlation beyond the local hidden variable model. So in view of these two possibilities, it is hopefully, obviously, clearly that if they do local things, they should not be able to prepare an entangled state from nothing. I think this is reasonable to say that, well, no matter what you think your entangled state is, this should not happen. The statement, there is another thing to mention as well. Even if they already start with some entangled state, to generate an entangled state from a product state like a zero-zero state should not happen if you demand that the catalyst, we call the green state, the original entangled state that they share, if you have to regenerate that state at the end of the day, they should not be able to gain an entangled state out from nothing if the measure of entanglement is at least additive. They shouldn't just gain something from nothing. They gain something from something, but the something has to come out as well. So this also seems to be a reasonable thing to say that this shouldn't be possible under quantum mechanics. If it's possible, then they can repeat this game again and again and generate a large amount of entanglement from the same initial state. And this clearly shouldn't happen in any reasonable theory of quantum mechanics. The statement of the embezzlement of entanglement is that this forbidden transformation, if you allow any small amount of approximation, will become possible. In fact, any state can be embezzled to any accuracy if you have the right initial starting state. That's the statement of embezzlement of entanglement. So I'm going to go through a slightly more precise definition what this means. I will label the system in which the state 00 is living. I will label them as A prime and B prime, and the catalyst that they're going to use will live on the system A and B. Mathematically, we say that you tell me how precise you want this approximation to be. You choose epsilon. Anything bigger than 0 will be accepted. You choose a dimension for the system that you want to perform the embezzlement. You choose A prime, B prime. These are 2D dimensional systems. You pick your favorite state that you want the two parties to embezzle from 0, 0. Then I can tell you the dimension of the catalyst is capitalized N on each side, what state they will need to choose, what local operation they would need to perform in order to generate a state. So this is what they can obtain with the above setup. And the promise is that the final state will be epsilon close to what you think should not come out, which is the catalyst together with the state that is entangled on A prime, B prime. The approximation here, you can take it as 1 minus this overlap between these two states.
And Debbie, just a question of motivation. Can you motivate again why the language catalyst?
Sure, because it has to come out approximately at the end of the day. It has been brought in to do the transformation, and it is returned as an output at the end.
Oh, I see. So, okay, yeah, because a chemical catalyst doesn't get used up in the reaction. I see. Okay.
If it gets used up, then it's not so surprising at all.
Yeah.
The surprise is that it's almost not used up.
Yeah. Okay. And I guess you'll go into what you mean by almost and so on.
That's right. And so let me, of course, give credit to the people who came up with the possibility. I think the courage to ask a question that seems clearly impossible is one of the biggest achievements in the original work. I always admire that, the courage to ask for the impossibility. In fact, their work is a little more strong than the theorem that I put down there. They have a one catalyst that fits all possible state that you want to embezzle situation. It's quite surprising that you can pick the catalyst to be a universal catalyst for all state that you want to embezzle. I can show you what it is. It in the Schmidt form in two parties. The Schmidt coefficient is scaling like 1 over square root k. Sorry that I don't have the square root written down there. And then you rescale. And the analysis is not too hard, but I will show you something a little easier in this talk, which is not universal. You need to know what is the initial and the final state before you can write down the catalyst. But that's allow me to give the entire proof how it works within 5 minutes. So remember, we want to drive the transformation from 0, 0 to a state psi. And we're now going to pick the system A and B and the catalyst.
Debbie, when you have a moment, there's a question here from the audience. I can ask it. The question is from Xi Zhong. Is phi sub A prime B prime? I think it might be the previous, or I guess you have it here. Yes, it's the purple thing. entangled, what does the index epsilon mean?
So yes, phi is entangled. And you can pick any entangled state. And epsilon means that the two sides on the approximately equal should have just inner product as vectors in Hilbert space, at least 1 minus epsilon.
Okay, yeah, then.
Then everything, there's no physical way to distinguish between these two states better than a bias, roughly epsilon itself.
Okay, gotcha. I guess the magnitude of the inner product.
Right.
Good.
Right. Okay. So then now we want to choose this green state, the catalyst. The system that we choose to hold the green state is actually n copies of the system that you want to drive the transformation. So we pick A to be n copies of A prime. We call that A1 through AN, and the system B to be n copies of B prime, and we label them as B1 through Bn. We'll work out what small n should be. I can tell you up front, it's actually 1 over epsilon. So the state, I can describe it by drawing two concentric circles. Alice holds one circle and Bob holds the other circle. On A1, B1, I will have a state 0, 0 there. On A2, B2, I'll have a 0, 0 state there. And all the way up to AR, BR, I have a 0, 0 state there. On AR plus 1, BR plus 1, I'll have the state phi. And similarly, all the way through AN, BN, I'll have the state phi. So now in this circle, I have R copies of 0, 0 and N minus R copies of phi. The crucial thing is to then take a superposition over R from 1 through N minus 1. And this is the catalyst that the two parties should have in their hands in order to perform this forbidden transformation.
And you can pick any n at this point?
Yes. And we will see that n equal to 1 over epsilon will be enough to enable the approximation. So this is the definition of the catalyst. We need to do the renormalization, of course. We need a proper vector in the Hilbert space. And then I will position the system that I want to do the transformation at the gap. A prime, B prime, I place it there. And remember that it starts with 0, 0 state, and I'm going to show you what are the transformation U and V that I'm going to choose. It's very suggestive in the diagram what I'm going to do. I would want to permute cyclically around the circle. I take A prime, B prime into A1, B1. I take A1, B1 into A2, B2, and so on. And all the way out, and A and Bn should be permuted out to A prime, B prime. Now, if you think about it for one moment, it is actually a local operation. Alice permute her A's and Bob permute his B's. And this is actually local unitary. And if you check what's going to come out, on A prime, B prime, you're going to have a copy of the state phi that has come out from A and Bn. On A1, B1, it is a 0 state that has been purple before and is now shifted in there. On A2, B2, the state from A1, B1 is now living there, and so on and so forth. So nothing actually changed until you reach the R plus 1 system. Now it changed from a state phi to a state 0, 0. And then from the R plus 2 system onwards, nothing changed. So in other words, the change happened at the two boundaries at the circle. One of the boundaries is always A prime, B prime. The change is always from 0, 0 to a phi. The other place where things change is the R plus 1 system. It changed from phi to 0, 0. But the boundary shift around depending on which term we're looking at. And so if you check what actually really happened in the transformation, the 0, 0 state did change to the phi as we wish. And the remaining state changed from a shorthand writing like this to just one in which every term gain a copy of 0, 0 and lose a copy of phi. Every term change, but every term becomes the previous term. So in the end, this whole green state, which is my output catalyst, is actually nearly the same as before. It's only missing only the two boundary terms differ. So when we took the inner product, it is actually 1 minus 1 over n, or 1 minus 1 over n minus 1. It doesn't really make a big difference here when n is large. So all we need to do is to choose n being roughly 1 over epsilon to achieve the epsilon approximation that we wish to obtain. I hope this is convincing enough.
No, this is really neat. Yeah,
So
I guess the trick is that when you slide things 1 over, it all looks the same except for the boundaries.
yeah, so this is how it works. Something that looks almost impossible as a first principle actually can be done quite easily. And so to summarize how the scheme works, you prepare this in the catalyst that has an kind of an indefinite number of the initial state and also an indefinite number of the final state that you want. The initial embezzlement paper talk of the entangled state that you embezzle as the reason why you want to do the embezzlement. Here, what I want to advocate is that what we want to achieve is to perform a forbidden transformation with the help of a catalyst. The forbidden transformation is from 0, 0 to phi because the two parties are only allowed to perform local operations, and therefore they're not supposed to change the entanglement structure of the system that they're transforming. But because of this catalyst that has an indefinite number of EPR pair in there, they certainly can do it with good approximation. Quick bookkeeping on the dimension of the system is the number of the dimension grow quite quickly with the approximation. But if you count the number of qubits, roughly speaking, the size overhead that you need to do on the catalyst is all the 1 over epsilon. It doesn't matter what is the initial state and final state. If you change 0, 0 to eta, it still works. It doesn't matter how many parties there are. This is one small advantage of our scheme compared to the Van Hayden scheme. The scheme relies on what we call the Schmidt decomposition of bipartite pure states, and we do not need the Schmidt decomposition for the scheme to work. So you can have as many parties as you wish. You just have more and more concentric circle in the drawing. And it doesn't matter why you cannot convert eta to psi. This method, as long as you are allowed to do cyclic permutation in the system, it will work. So this allowed me to get onto the first application of the idea to embezzle. I want to discuss, it is the first time I actually understand how we can perform macroscopically control coherent operation in the lab. And after this, if I have enough time, I will talk about a more recent application on belt inequality that cannot be violated with finite amounts of entanglement. And then I won't be able to have time to talk about the quantum reversion theorem, which is actually historically the first application of embezzlement done right at IBM itself in around 2001. So to abstract things a little further, we should think about the local operation as restricted set of operation. When we restrict the operation, we will start to see there are invariances in our system that in physics they are called conserved quantities. Charge, spin, energy, they're all supposed to be conserved. Embezzlement, the way you have seen it just a few minutes ago, should be considered a generic recipe to allow us to approximate this forbidden transformation based on superselection rules. In short, if you can't convert eta to psi directly, because eta and psi contain different amount of a conserved quantity, you can, but meanwhile, you can do cyclic permutation. Then you can ask if you can prepare this initial state, which has an indefinite number of the conserved quantity R of one state and n minus 1 of the other state, and then there is a proper superposition. Then the transformation from eta to phi can be performed, similar to what we have seen before. It's just the same mathematics with the cyclic permutation. Meanwhile, the state that you ask this catalyst with an indefinite number of the conserved quantity will be returned with approximation, very good approximation. So it looks like we have violated the conservation law, but we haven't. The actual state we have here has the correct amount of the conserved quantity, but it approximates a state that looks like the conserved quantity has been broken because eta seems to have gone to phi and the initial catalyst is sitting around. So it's a very strange situation, but it's actually real and is allowed. Then not only you can do that.
So the quantity in that case is no longer strictly conserved, but it's almost conserved, right?
The opposite. The quantity is actually exactly conserved because we have only we label our system, but it approximates a state which has a different amount of the quantity. So the violation is an illusion. We have an illusion that we have violated the conservation law when the conservation law actually has been holding strictly.
Mm-hmm.
Now this is.
And sorry, could you say again a little more about what the quantity is in this example?
We have seen the example for entanglement. When 0 become an entangled state, and you can pick the entangled state to be the maximally entangled state. So it is one EPR pair worth of entanglement that we have, that we seem to have violated. Like suddenly we have one additional EPR pair in the system. And we actually have not gained any entanglement. It has been taken away from the catalyst. The catalyst has lost some entanglement, but it doesn't look like it has because it looks so similar to what it was before.
Okay, I see. Mm. Yeah. Because yes, okay, yeah. Because you almost have this macroscopic state, and I guess that's where the driving of operations is going to come in. That's very nice. Good.
And in fact, this was what I slowly realized how it connects to the lab when I was visiting IBM in 2008, and when I first gave this result, a talk on this result. I added the next few slides to show what I learned from this exercise. So the interesting thing is that not only it is possible, you can perform it and not perform it in superposition. If you're allowed to label the terms. So what we wanted to do is to convert eta to phi with the help of this catalyst. Now, suppose we also have a state gamma in the same space, A prime, B prime, that we don't want to convert. So we want phi to gamma to remain gamma. And we happen to have a label 0 to label gamma and 1 to label eta, so that we know that if it is 1, then we want to drive the conversion. If it is 0, we don't. Then in the end, because in the second term, the catalyst come out roughly the same as before, we can approximately factor it out from the two terms. In the first term, gamma, psi come out exactly the same way. In the second term, eta, psi come out roughly phi and psi. So we can roughly, approximately factor the catalyst out so that the first part of the state look like it has coherent be transformed. Now, this allows the following exercise, mental exercise, to be done. There is one level of abstraction because now I'm not counting the number of copies. I'm trying to think about spins in the system. I actually did half of my PhD as a student at Almeda, working on NMR quantum computation.
Oh yeah.
So I'm perpetually sentimental to spins. So let me call the ground state spin 0 and the excited state, the spin up, the 1, the spin is labeled by system S. Now the NOT gate says that if I have an A0 plus B1, I would end up with an A1 plus B0. But anyone who have heard of the conservation of spin should be a little bothered by performing a NOT gate there, because it looks like the spin number has changed if A is not equal to B. So this looks like a gate that we cannot perform. And in fact, in NMR, what we do is to generate from the variant probe what we call a laser beam. I hope I don't say anything wrong. I'm actually a theorist. I never walk into the lab. So the laser beam has a number of photons in there, say R of them. And my understanding is that if you have R photons together with downspin, you can turn it to the upspin with one fewer photon in the laser beam, with some form of spin-like interaction that we can drive.
And this is a coherent state or a Fock state type of excitation R?
This is a crucial question. What I want to say is that the way I have written it will not allow us to perform the NOT gate. The reason is also very simple, because if your electrical company track how much energy you have used in the variant probe, they will realize that if you have initially the A0 term, the output laser beam will be missing a photon. If you initially is in the B1 term, the output laser beam will gain a photon. So if someone can make a photon counting measurement in the output beam, they will find out which term you're in, and thereby decohering your spin system in the end. What we need is actually a Fock state. Not Fock state. What we need is to have a superposition of different values of number of photons. The way we talk about having different number of EPR pair versus the zero state earlier. So what we want is actually an indefinite number of photons going into the spin sample. I remember it looks almost like a small little finger. There's a little glass tube with the liquid inside. You want an indefinite number of photons going into the sample, so that when the photon beam leaves, it either come out with one photon missing at every term, or one photon gained at every term. But either case, the output beam is close to the input beam, so that no one can tell which term your spin system is in. And in the end, you can approximately factor it out to get the state that you want. It's actually a revelation at the time. I realized, oh, actually, this is what they do in the lab. And I know that it's an oversimplification from a theorist point of view. I know that in the lab, they use coherent state and there's some differences, but at least the spirit is similar. The idea is that you want to intentionally take a catalyst that has an indefinite number of the conserved quantity in order to approximate a violation of the conservation law.
Have you looked into what happens in the case of the coherent state, just out of curiosity?
Yes. In fact, it was a lunch discussion when I was at Amazon. The coherent state gives better approximation, but a little harder computation. And I think people like the coherent state because it's generated easily, physically. But this the equal superposition makes it obvious why it works, because the mathematics is trivial. The easier the better, I think. Sometimes just conceptual understanding of an idea. So this concludes the first application. I just find it somewhat surprising to connect these two subjects. They don't seem to be the same thing, but the mathematics is actually very similar. Then the next connection is to a subject called the Bell inequality that a lot of us are familiar with on non-local games. In fact, there are 3 titles of this result. We will show why there are Bell inequalities that are finite, clearly finitely stated, but that cannot be violated maximally with finite amounts of entanglement. This is the physics way to say it. If you're from computer science, you will say that there is a non-local game that cannot be played optimally with any finite amounts of entanglement. The more entanglement, the better. If you're a mathematician, you will say that the set of correlations, concorrelation, is actually not a closed set. And we will see this result through a construction using embezzlement. I would say this from the viewpoint of computer science, because I find it a little more natural to talk about. So I will briefly summarize what is a non-local game. In a non-local game, there are a bunch of players, K of them here, that will interact with a referee. These players can coordinate a strategy before the game, but once the game starts, they cannot communicate anymore among themselves. And once the game starts, the referee will draw a catapult of questions. So each of these items is a question. Together, I call it a query. The distribution of the queries is known to the players. And after the referee draw the query, each player will receive one part of the query. And when they receive the question, their own part, they have to supply the referee back with an answer. So these double lines represent classical data using the Nielsen and Chuang convention. Now the referee collect all these answers and will make a decision. Do these players win or lose? So condition on the query and the joint answers, the referee will announce, did they win or lose? And the players, the goal is to win the game as a team with the highest possible probability that they can do. And in the subject of non-local games, the main question is, does entanglement help improve the probability of winning? Here is an example of a non-local game called the GXC game, in which there are 3 players. The questions each has 2 possibilities. It's either a small x or a small y. So each of them receive a binary question. And the queries do not come from all 8 possibilities. There are only 4 possible queries. They always come with an even number of the symbol y and an odd number of the symbol x. And for all purposes, assume that these 4 possibilities are drawn with equal probabilities. Now the answers are binary as well. It's either a 1 or a -1. The winning condition is set by saying that if the query has no occurrence of y in it, then the product of the 3 outcomes should multiply to 1. But meanwhile, if at least if they have 2 of the y's and 1 of the x among the questions, the answer should multiply to -1. Now, these winning conditions are constructed so that if the players have each of the player has a deterministic strategy, which says that if I receive x, I'm going to answer a equal to -1 or 1. If they have a specific plan, x correspond to a certain answer, and y, the question y, correspond to a certain definite answer, then at least 1 out of these 4 winning conditions will not hold. They are not consistent with one another. So the winning probability is no bigger than 3/4 for deterministic classical strategies. When they share randomness among them, it's not going to help, because the randomness is allowing them to have winning probability, which is a weighted probability, weighted average of the deterministic strategy. And so without entanglement, the winning probability is no better than 3/4. But with entanglement, in particular, if they share what we call a GC state, which is a superposition between 0, 0, 0 and 1, 1, 1 in equal amplitude. And each party, upon receiving the small symbol x or small symbol y, find out the eigenvalue of sigma x or sigma y in their own laboratory and answer the eigenvalue 1 or -1, the winning probability is actually 1. So this is a simple non-local game in which entanglement clearly help. Furthermore, this game has a nice feature, what we call rigid. It means that if the parties win with probability very close to 1, they must have followed through a strategy which is very, very close to this particular one, sharing a GC state and measuring the eigenvalues of sigma x versus sigma y. If they win with very high probability, close to 1, then they must have essentially done the particular, they must have followed that strategy up to local isometries each. Here's a short vocabulary a dictionary that translates between non-local game and Bell experiment. But for the interest of time, I won't go through it here. The two concepts are almost identical to one another, with some very small difference in what we call the payoff function versus the winning probabilities. The motivation to study non-local game for the computer scientists is that it allows us to study a large complexity class called interactive proof system, in particular in the multi-party setup. The non-local game with entanglement simulate the unit interaction in the interactive proof system. And in fact, earlier this year, there is a major breakthrough in understanding this complexity class with multiple players called MIP star equal to RE. Among the physicists, the main motivation to study non-local games is to see whether local hidden variable model is violated or not. If it's violated, we believe that we are having a physical theory of quantum mechanics. But the violation of Bell inequality itself does not verify that we have quantum mechanics as a quantum system. Rather, it rules out local hidden variables. If people already believe in quantum mechanics, then the study of non-local game allows them to construct cryptographically secure quantum key distribution scheme through the rigidity feature of some non-local games. And finally, I should add one other item. For the mathematicians, the interest in non-local game come from the fact that the closure or the lack of closure in certain set of quantum correlations is connected to the resolution of a long conjecture called the cone embedding conjecture. And that was also recently refuted by the same result in early this year. The same result that shows the interactive proof system in multi-party with entanglement assistance is equal to RE. So in this application of embezzlement, we have a more focused goal. We want to know how much entanglement is needed to win optimally at finite non-local games. It has been conjectured around 2009 that there are finite non-local games that nonetheless require more and more entanglement to have higher and higher winning probabilities. It wasn't easy to prove this conjecture. It took about 8 years for the first formal proof due to Will Slofter, whose office is actually next to mine at KC. And then soon afterwards, my other colleague, Vern Paulson, and his group come up with a second proof. These proofs were existential at the time, and they were not. It was not clear how it's not clear what is involved in physically requiring more and more entanglement to win with higher and higher probability. So what I'm going to show is a construction which essentially forced the two parties in a non-local game to embezzle. And we will see that embezzlement has a property that the bigger the catalyst, the better the two parties can embezzle. And they can never do this perfectly because it's not allowed, it's impossible, it's forbidden. And so this allows us to, and we will try to see how to embed the winning condition in forcing the two parties to embezzle, in order to show that the more entanglement you have, then the higher probability it is for the two parties to win. This is a line of research done by myself and Xiangfeng Ji and Thomas Vidic a couple of years ago, and there was a simplification by Andrea Coladangelo last year. So embezzlement is a very interesting phenomenon because it is a no-go in the perfect. If it's done perfectly, it's a no-go. It's absolutely not allowed. But when you allow approximation, suddenly it's becoming possible. So we should think about it as a phenomenon that has very poor continuity, how well you can do it. And it is not hard to show that if the initial and the final state are differing from one another in a certain quantity of the entanglement, then dividing that quantity of the entanglement over the log of the dimension of the catalyst together with the log of the dimension of the initial system, the whole quantity square is essentially a lower bound to how big the error has to be. So with finite dimension, you can never do an embezzlement perfectly. But furthermore, here we have a very clear quantitative trade-off between the system size for the catalyst and the error we can achieve. So our first approach in 2008 to show that more and more entanglement would enable bigger and bigger winning probability comes with changing the definition of the non-local game slightly. What we have done at the time is to allow the referee to send quantum system to the players and allow the players to send quantum system back to the referee, and then the referee will be allowed to keep a quantum system as well. And together, the referee will collect all the quantum system from the players and make a joint measurement on all of them together and decide through a binary measurement whether the players win or lose. The question is, again, does entanglement help and how much is needed? If these systems are all finite dimensional, do we ever need to have more and more entanglement for the parties to win with high and high probabilities? And here is a game, a very simple game that we can just write down that will not be able to be won with finite amounts of entanglement. So since I only have two parties in the game, I just label the two question system as X and Y, and the answer space as A and B, and then the space that they share, the state that they can share before, live in E and F. The state that the referee start out with looks like a product state 0, 0 on X and Y, superposed with an EPR pair 1, 1 plus 2, 2 living on X and Y. And the referee knows which term is which by having a 0 or a 1 in his system R. And these two possibilities are in quantum superposition with one another. So the joint state is pure on R, X, and Y initially. Then the referee gives the state, the three-dimensional state X to Alice and the three-dimensional state to Y to Bob. And at the end of the day, after he receives A and B from Alice and Bob, he will make a measurement with two outcomes. It is a projective measurement. One of them will project onto the GXC state, 0, 0 plus 1, 1, 1 in equal superposition, or otherwise, the other 7 dimension in the 8-dimensional hyperspace. So if the two parties are to win this game, you can compare the two states. And what they need to do is to convert the 1, 1 plus 2, 2 into the 1, 1. But they have to do it keeping the coherence with the first term. They can't just throw the 0, 0 plus 2, 2 away and replace it by 1, 1, because that will break the coherence, and then they will only get the GXC state with probability half. What they need to do is to coherently convert the 0, 0 plus the 1, 1 plus 2, 2 state into the 1, 1 state. Now, you can see why this connects to embezzlement, because one possible strategy is for them to condition on being in the 1, 2 subspace of the incoming quantum system, perform embezzlement. In fact, in this case, they reverse embezzle the EPR pair to become the product state 1, 1. And if they have a bigger and bigger catalyst, as we have seen before, the small symbol, the small n, which should give rise to the error 1 over n. If n is bigger and bigger, then they can win with high and high probability, but they will never get there because perfect embezzlement is not possible. So this is one possible strategy that allows them to use more and more entanglement to win with high and higher probability. Sorry,
We're good on time, by the way. So if it's okay if we run a little bit over.
Yeah, and sorry, I hesitated for a moment because I wondered if I was actually online. Okay, good.
No, I know. Without a live audience, it's always a little bit harder to get more feedback.
Right,
No, we're doing
right,
good.
right. So good. Well, we are actually very close to the end of it. If you look at the number of slides, so we're good.
Okay, I see.
But it is actually relatively. So it is clear why more and more a bigger and bigger catalyst allow them to win with higher and higher probability in view of what we have just seen earlier in the talk. And it is not hard to prove at all that the winning probability is upper bounded by 1 minus a function that depends on the size of the dimension of the state that they share. This is what I find very interesting. The proof is actually very basic linear algebra that takes no more than like the bulk of 1 page, compared to the very complex paper that Will Slough just sent off to prove a similar result in the non-local game setup. Of course, in that case, the question and answers are classical. So this was the result that we have when the questions and answers are quantum systems. The question is, can we turn this game into a proper non-local game when the questions and answers are classical messages? In 2012, Redgov and Vidic converted half of the game to classical, but it's really difficult to turn the initial state into a classical set of questions. And we finally found a way to do it in the end of 2017. The way we have done it is to take the referee and convert the referee to become a third party, so that the distribution of the initial state become the entangled state that they should share before the game. And then we have a very simple idea to turn the final projective measurement to check whether they have a GC state or not to some simple sets of questions and answers based on the rigidity of the GC state that we have seen earlier in this talk. But now the question is, why would the three parties, Alice, Bob, and Victor, will prepare the initial state as you wish they do? Of course, they may not do what you want them to do. The idea is to add a real referee in the non-local game that will send them questions and that will collect answers to force them to obey the original quantum game. But now the questions and answers are all classical. As we see, the time is getting close to be 1 o'clock, so I will not go through the detail of this construction. But it turns out that it's also not so hard to show that this non-local game carry all the initial feature of the quantum game. And we can show that with 3 players, very small number of questions each, very small number of answers.
Debbie, sorry to interrupt you. I missed the question earlier. There's a question from a student here in the audience who's asking again, what does it mean to have a ket 2? Because he says, well, I know what ket 0 and ket 1 are for a qubit, but why is there here a ket 2?
We allow the system X and Y to be 3-dimensional in this game.
Yes, you mean a spin 1.
You can have a different kind of system. You can have, for example, photon number states, 0, 1, or 2, depending on whether they have no photon, okay. 1 photon or 2 photons.
Oh, yes. Photon states, good. Okay, yeah, so it's actually 2 excitations. It's 2 photons.
Right. So here, the essential feature is just that the system size of X and Y is 3-dimensional, and the answer space is 2-dimensional. A and B should be 2-dimensional. And it's a finite game. I mean, it's a finitely described game. We want to turn this initial state, very simple state, into the final state, which is a GC state. And this is a very clean description of what we need to get done by Alice and Bob. And it turns out that they must embezzle in order to convert the state from the left-hand side to the right-hand side.
Good. Thank you.
Yeah. We didn't prove that they must embezzle. We proved a bound on the dimension. But recently, I obtained a proof with Ian Charlesworth from Berkeley. that they must embezzle. So in short, we can obtain a non-local game with 3 players, 12 questions each that they may receive from the referee, and very small number of bits that they may ever need to answer, which we know that they can win with probability at least 1 minus epsilon if they share all the 1 over epsilon qubits. And it is also necessary, if they want to win with probability at least 1 minus epsilon, they must share at least epsilon to the power of minus 1 over 32 qubits. And that is a trade-off exponentially stronger than previous result. And it is clear why they must share a lot of entanglement, because they need to embezzle. Physically, it's an interesting observation, because they can have the experimentalists can set up a finite setup in the lab that would test a server, whether they can test the server, that they can test the dimension held by the server. If the server are actually 2 separate parties, they can verify that the 2 servers must share a certain amount of entanglement, or have a certain number of dimensions. You use the same setup, and you need to repeat the test again and again to lower bound the probability of success. But you do not need to make the setup bigger and bigger. You have the same lab. You repeat sequentially the test to have confidence of how much entanglement they share. And then last year, Coladantula has a slightly simpler construction that preserves the number of parties and has few questions and a very similar trade-off in the winning probability and the dimension. But I won't go through that because I'm slowly running out of time. But if I may just add one more small little result, I want to say we find one further very surprising connection to something that we did not suspect before based on embezzlement. It is that you can define quantities on quantum state, and you can show that they cannot be very continuous as a function of the state. If the property is this quantity has a very obvious property, again, that is because of embezzlement. And let me just quickly say this in 1 or 2 minutes what this means. Suppose we label the set of density matrices with the script D on D dimension, small d dimension, and quantities like entanglement or spin or charge be labeled by F, and this is defined on density matrices of any dimension. If this quantity satisfies 3 obvious properties, which means that if you have 2 systems, you have a product state on the 2 separate systems. These are 2 separate product states. Then the quantities on one system should be added to the quantity on the other system if you have a product state. Charge has that property, spin has that property, entanglement has that property. And if that quantity is not a constant, as long as it's different on different state, on at least 2 different states, and if the quantity is invariant when you relabel the system, which for all purposes is the case, then we have the following result. This quantity can never be too continuous as a function of the density matrix, in the sense that if you have 2 different density matrices on capitalized D dimension, then you can bound the difference of the quantities when you change from one state to another by the trace distance between these two density matrices. Now, if we have a tight bound here, the quantity is continuous. But what we find is that the factor of log the dimension of the system must be raised to a power at least 1 for this inequality to hold. And that's because of embezzlement.
And what would happen if F is not additive but multiplicative? Like if you had the expectation value of ZZ, wouldn't that be multiplicative?
It will be, but the log of that will be additive.
Okay, so you're saying that you would just cast that into... but does that imply that if the log of it is not continuous in this way, then do you know what I mean? Then the original quantity, which is the exponential of this, would be would also suffer the same?
Yes, basically additivity and continuity are actually in direct conflict with one another. That's what we find out. It is rather surprising. We do not see any connection before this little proof that we have.
And would you suspect that multiplicativity and continuity are in direct conflict as well, or are those not in conflict?
Once you take the log, they will be in conflict. So there is some bound, but it will be a weaker bound.
Okay, so maybe it's better, but not perfect.
That's right. In a sense, it's just additivity is a very natural demand because most things are extensive. Most things physically are extensive, and so
Yeah.
and the reason is exactly what we have seen earlier too. I did not have time to prepare slides, but I wrote this by hand today.
Oh yeah, that's great.
You start with this state with a certain quantity defined, which is the sum of the two things. You have the quantity on 0 plus, I forgot the plus there, the quantity on the state side, which is the catalyst. But because the quantity is preserved by cyclic permutation, so it is equal to the same quantity after you apply the attempted embezzlement. And meanwhile, this state is very close to the state which has the final state coming out together with the catalyst. And when you calculate the quantity here, it is the quantity of the final state added to the quantity of the catalyst. And the two are solidly different by f on the quantity. It was one e-bit of entanglement earlier, but it can be any other quantity, like one spin, one charge. And meanwhile, these two states are similar. So we know that two similar states nonetheless can have a constant difference in the quantity, which tells us that they cannot be very continuous. Somewhat unexpected, but we have to live with it because we proved that, so we can't run away from it.
And for the more uninitiated of us, can you maybe clarify the LU notation?
Sorry, it is local unitary. So it is the restricted operation that is being applied there.
Awesome, great. I have a funny question. Why is the epsilon on the approximate sign on the right of it and not on top of it?
I probably should have put it on top. You
were consistent in your notation. I'm just curious, but maybe we'll say that after the talk.
It was my little program that would not allow me to put it on top of the approximate sign.
Oh, okay.
So when I do it by hand, I follow the same convention.
Yeah, I mean, that's perfect. If you're consistent, it's great. Yeah, I just didn't know if it meant something.
But to reassure my host, I'm finished here. So I just leave a bunch of open problems here, except that the last one has been resolved recently. Item number 6 has been resolved. The early one has not been. So I'll stop here. And thanks for your attention.
Okay. Wow, wonderful. Thank you for this really great and interesting talk with this A+ title. I know we had many questions during the talk, so that if there are any final questions, feel free, folks, to post them in the chat, and I'll get those over to Debbie. And maybe, Debbie, I'll just open it up for a minute if you want to say any final words, or say, where you think the next directions might be headed in this field. And I'm guessing that has something to do with the open questions you've posted here.
Well, we like the minimal example, like how big the game has to be for this to hold, is around. We show the example for 3-dimensional input for each side. We wonder whether the same hold if you restrict the dimension to 2. My initial motivation is this game called the I3322 game. We have a lot of numerics. We have a lot of understanding. I never know if this is also a counterexample. We have been thinking about this for 7 straight years.
Wow.
Never resolved. I'm a very stubborn person. If I can't resolve a problem, it never get off my mind. So it's keep me awake at night. And more recently, this slide of open problem was written last year. More recently, we're also wondering if embezzlement, perfect embezzlement with C-star algebra could be an explanation why the cone embedding conjecture doesn't hold. This is a very wild guess. We do not know. We're not sure. It looks maybe, maybe not, and we are still investigating.
Yes. That's a puzzling question if it's taking 7 years. So that'll be very exciting when you figure that out. Good. And I think, let's see, okay. Yeah, I think with that, if there are no other questions, I'd like to thank you again for coming and accepting our invitation and coming to the seminar series and for the wonderful talk. And I'd like to thank the audience for tuning in. This talk will stay recorded and live, so you can go back and look it over. And come back next Friday. We will have another one excellent talk coming up next week at the same time, Friday at noon. So with that, Debbie, I want to thank you very much. And I'd like to thank folks very much.
Thanks for having me here. Even virtually, it's nice to be visiting IBM again.
I know, I wish we could do this in person. So hopefully sooner than later.
Right.
All right, well, thank you everyone, and we will see you next time.